Hello and welcome to the video presentation on the development of a modular HPC for advanced computer engineering at the University of Greenwich. The aim of this project is to design and develop a prototype of a modular HPC. The final prototype should have the ability to perform exercises such as DNA sequencing, password cracking, weather predictions, and more. This presentation is broken down into 8 chapters. We hope you enjoy the video.
To develop the system's design and architecture, we had to work with components provided by the university. We were provided with 10 ASUS CS8 motherboards, 10 SD cards, multiple 220 watts PSUs, a 5-port switch, and a Raspberry Pi 4 Model B. To meet the modular criteria of the project, a single module consists of 4 nodes, 3 containing a motherboard with its corresponding PSU, and the 4th node being the head node, which holds the single board computer and the switch. Consider figure 1. Due to the switch having 5 Ethernet ports, 3 ports are taken by the motherboards. One port is taken by the single board computer, leaving an extra Ethernet port to allow the entire HPC module to be connected to another copy of the HPC module in a daisy chain configuration. This daisy chain can be extended to multiple copies of the HPC. Consider figure 2. The system's structure utilized a main configuration file, referencing 3 other separate files for managing the configuration, packages, and services. During the installation of various packages, an error occurred with the Samba package, a critical component for network communication, because an incompatible version was downloaded for the system's architecture. Attempts to resolve this included rolling back the system, which did not give the desired results, and cleaning dependencies, but this step inadvertently removed essential components halting system progress. The group had to consider either transitioning to a new operating system or reinstalling NixOS. A comparative analysis of NixOS, Debian, Ubuntu, and Arch Linux was conducted to inform the decision. Given the limited progress made and NixOS complexity, the decision was made to switch to an alternative operating system, with Ubuntu being the selected replacement. This choice was influenced by Ubuntu's user-friendly nature, making it a practical option for those new to Linux, as well as its broad accessibility. It has efficient package management via apt and deb as a package format, and offers stable releases with extended support. Additionally, its substantial documentation and supportive community simplify troubleshooting. Ubuntu also emphasizes security in system integration and has a wide repository containing over 60,000 packages, further validating its selection.
Pre-boot execution environment is a network protocol that allows a computer to boot and load its OS using resources from a server rather than a USB stick or an SSD. The 3 main components of PXE booting are establishing a DHCP server, TFTP server, and network file system. In this project, the head node is configured as the DHCP server, TFTP server, and the NFS server. Being displayed right now is a directory tree of all files relevant to PXE booting. All required files for PXE booting are stored in TFTP boot, which is shared via the TFTP server. Within the TFTP boot folder, there are 2 main folders. Firstly, the Ubuntu folder contains all necessary files to run the Ubuntu Live installer on compute nodes. Secondly, the pxelinux.cfg contains a default file which specifies the boot menu. The TFTP boot folder also requires some files from syslinux library, which are essential utilities. Firstly, all computers in the HPC setup must be able to communicate with each other. Here, the dynamic host configuration protocol is used to allow the compute nodes in the network to be dynamically assigned an IP address. This removes the need to perform static routing and addressing on each device of the HPC. To set up a DHCP server, we have configured the dhcpd.conf file and have specified the IP of our network and the netmask. Additionally, we have specified the range of IP, the router, lease times, and the next server parameter, which specifies our TFTP server, which is the Raspberry Pi. Finally, the file that the clients request for booting UEFI systems, syslinux.efi, is also specified. Therefore, upon obtaining an IP, syslinux.efi is fetched by the compute node. Trivial File Transfer Protocol is a lightweight protocol used to transfer files between devices on a network. The TFTP server sends the files required for booting located in TFTP boot in small packets to the compute nodes using UDP port 69. The compute node receives the packet and loads the file as the operating system. In the TFTP configuration file, the root directory for the server and the interface used for communication are specified. After selecting the operating system from the boot menu, the images and kernel files must be loaded. Therefore, NFS is set up and it allows a system to share directories and files with others over a network. This is done by adding the directory that is needed to be shared as a shared directory across the network. An ISO image of Ubuntu 20.04 installer is installed and mounted. It is then copied to the Ubuntu directory. This directory now contains all ISO files necessary to install the operating system on the compute node. Being displayed right now is a PXE boot menu configuration file. We have specified just one boot option, which is Ubuntu 20.04 NFS boot. Along with that, the kernel file path and initrd file path relative to TFTP server's root directory and the NFS root path located on the server are specified. We have also configured to obtain IP via DHCP and netboot using NFS. Finally, this illustration provides an overall overview of the PXE process. When the compute node powers on, the network interface card sends a DHCP request to the head node. The head node sees the request, assigns an IP using DHCP. The syslinux.efi and other files are shared to the compute node. These files are then loaded and the boot menu is shown with an option for Ubuntu 20.04 on the compute node. After selecting Ubuntu 20.04, NFS is used to load the initrd and VM-Linux files into the compute node. All required files and services are then loaded from head node via TFTP server. Installer loads in and user can run installer to install Ubuntu on their compute nodes.
OpenSSH is a powerful collection of tools for the remote control and transfer of data between networked computers. OpenSSH is a freely available version of the Secure Shell protocol family of tools for remotely controlling or transferring files between computers. Traditional tools used to accomplish these functions, such as Telnet or RCP, are insecure and transmit the user's password in clear text when used. OpenSSH provides a server daemon and client tools to facilitate secure, encrypted remote control and transfer operations, effectively replacing the legacy tools. To use OpenSSH, we would need to install the OpenSSH server and configure the firewall to allow SSH connections. Next, we generate the SSH key and copy the key to the computing nodes on the network. We have used a passwordless configuration for SSH for easier access to computing nodes. Application of Slurm Workload Manager. Slurm is a highly scalable and flexible workload manager used primarily in HPC environments. It allows users to effectively manage and schedule computing tasks across a cluster of computing nodes. A job typically includes details such as an executable to run, required resources, and any specific job parameters. Slurm manages tasks, separation, and allocation to prevent processing errors through a combination of job parameters, resource management mechanisms, and scheduling policies. Slurm provides mechanisms for inter-task communication and coordination allowing tasks to share data or synchronize their operations as needed. Tasks can communicate through shared memory, message passing, or file-based communication, facilitating collaboration and coordination among concurrently executing tasks.
Being displayed right now is a directory tree of all files relevant to the Slurm setup. All required configuration files for Slurm are stored in Slurm LL and L. Each node needs to be able to access the same files to complete jobs together. Therefore, a 16 GB USB drive connected to the head node is set up as shared storage. To set this up, the USB stick is formatted and a directory cluster fs to mount the USB stick onto is created. Next, automatic mounting is set up so that the USB mounts onto the directory on boot by editing the fstab file by adding USB's UUID details and other credentials. The directory is then exported so other nodes can access them. Similarly, we must also mount the drive on the compute nodes, and this is done by creating a folder with the same name on the compute node and adding this file to the compute node's fstab folder. In the Slurm configuration file located in the head node, we set the controller machine, cluster name, nodes, partitions, and resource allocation methods. Additionally, we configured cgroup support and whitelist system device files. The three configuration files, along with munch key, which is needed for authentication, are copied to the shared storage cluster fs, as compute nodes need to have these same files. We then copy the configuration files from shared storage into the compute nodes and enable munch. Munch is then tested by generating a key on master node and having the client decrypted. As it was a success, figure 6 was generated. Sinfo command is run on the head node. Its results show that a partition was created having two nodes under it as specified in the configuration file. Finally, an OR program is created, which generates 10,000 random datasets following a normal distribution, and density plots are created and saved as JPEG files. 50 instances of the OR program are performed parallelly, resulting in 15 unique plots to each job ID.
The process of defining the coding for this HPC is can be specified. The airflow required to dissipate the heat generated has to be approximated. Both the amount of heat to be dissipated and the density of air must be known. First, we will need to determine the required airflow to adequately cool the components. For this, you can use a rough estimate from the specification of our components. The case can use up to a maximum of 220 watts of power supplied by the PSU. Strictly for lower limit calculations, we assume that the heat load per row of our cluster is 220 watts. This would mean the efficiency of the components would be 0, which is unrealistic. However, it gives us a worst case scenario for the heating of our components. While different sources give nuanced methods for calculating cooling requirements, the cooling requirements were calculated using BTU per hour. BTU per hour is usually used in the definition of cooling power for HVAC systems. It is standard that 1 watt of power requires 3.412 BTU for cooling. So the required cooling capacity in BTU per hour would be as shown in the slide, along with its CFM conversion. For proper airflow, you need to ensure that the total cross-sectional area of the exhaust vent is equal to or greater than the cross-sectional area of the fan inlet. This ensures that the airflow is not restricted and allows for efficient cooling. You can refer to the slides for the calculation.
The HPC design has been inspired by Japanese joinery, creating interlocking ridges or box joints, allowing for the slotting of components to minimize the use of screws and glue. Additionally, the case has been designed to be a hybrid between a suitcase, allowing the user to transport the HPC comfortably by pulling, pushing, and lifting, and a shelving unit, dedicating an individual shelf per node, creating a separated and controlled environment for optimized cooling and organized arrangement of parts for inspection and troubleshooting. The design has been developed using Blender. The strategy was to design a single shelf and multiply that design by 4. However, the HPC contains two types of shelves, general and head. The shelf design has been based around the general shelf due to its containment of the largest components, a motherboard, PSU, SD card, and a fan, whereas the head shelf only contains the Raspberry Pi and a switch with some extra room for a small keyboard. Due to the tolerance margin of the laser cutter available, Three types of brackets were designed to ensure that a shelf holds itself securely. The truss holds the motherboard whilst elevating it to allow for thorough air circulation and storage of up to 2 SD cards. Instead of the motherboard truss, the head shelf contains a case for the Raspberry Pi and a switch to secure their positions. Lastly, all shelves contain a removable shelf handle for easy opening and closing, shelf stoppers to securely close the shelves during transport, and a top wall handle. The outer layer has also been initially designed in Blender. However, the designs had to be recreated in TextSoft Design as the laser cutter reads files in DXF format instead of STL. A double outer layer has been designed to hold the shelves together and allow the shelf runners to be installed with top and bottom outer layers securing the casing structure. Two types of rapid manufacturing techniques have been utilized: additive and reductive manufacturing. In total, 54 parts have been printed, with a total print time of approximately 177 hours and 30 minutes, which is equivalent to 7 days, 9 hours, 30 minutes, and approximately 1.4 kilograms of PLA, which in today's market can cost up to £40. Initially, acrylic was meant to be used for the case. However, a single board of acrylic of 1200 mm by 600 mm at 9 mm thick cost £90, whereas the same dimensions of plywood cost £26. Calculations have estimated that approximately 1.7 square meters of plywood was required to laser cut all necessary components for a single HPC. This equates to 3 boards of plywood. However, for safety, an order of 4 plywood boards was placed, coming up to £104. In total, 20 wooden pieces were laser cut for the shelves and 6 pieces for the outer layer of the shelving unit. Additionally, 4 pieces of 3 mm acrylic were cut as the shelf covers for the purpose of allowing the user to inspect a single shelf without having to remove the cover first. The top cover of the outer layer has been engraved with the course and team details alongside a QR code which takes the user to the GitHub repository of this project. The assembly process took 3 days. In total, to assemble the entire structure, including shelves, outer layer, caster wheels and suitcase handle, 122 M3 wooden screws were used, 74 of them at 15 mm of length and 48 at 20 mm of length. The final prototype stands at just under 70 centimeters tall, with a width of 37 centimeters and a depth of 27 centimeters. The total cost of materials and components comes up to approximately £220, which is within the £300 budget. The workload has been divided and delegated across the team according to the strengths and interests of each member. A visual timeline has been developed as a guideline of the project's lifecycle. Additionally, GitHub Projects was incorporated for further visualization using Kanban, table, and roadmap layouts. All project files have been managed and controlled using Git and GitHub for version control. In total, 5 branches were used: research, dev, design, video, and main.
Conclusion and future work. In conclusion, the successful completion of this project is due to the learning and utilization of multiple technical concepts. Concepts like network and routing, cluster management, distributed systems, cooling, and woodworking, among others, have aided in multiple stages throughout the project, varying from hardware to software.
Moving forward, several next steps could be taken. We have narrowed down to 4 points which would be implemented if the project was to be continued. Firstly, introduce containerization with Singularity, which offers a consistent and secure environment crucial for HPC's varied computational demands. Secondly, John the Ripper, an open-source password cracker used for the testing of password strengths and consequently the enhancement of security of the HPC. Thirdly, application of Prometheus, an open-source system designed for the monitoring of HPC's performance. And lastly, Jaeger, which with combination with Prometheus would allow for the tracing and identification of issues within the HPC system. We hope you enjoyed this presentation. Thank you for listening.